Hello everyone, I'm Luke Schrader, and I'm doing my lesson presentation on 2.2, limit of a function and limit laws. So limits essentially ask, how does the function behave near but not at a specific point? Which is asking what the output approaches as the input approaches some value. The way we write this is lim, which stands for limit. So the limit of f of x is L as x approaches c. I'm kind of getting ahead of myself here, but I wanted to show how these are evaluated. So you can evaluate them graphically by just looking. So if we look here, it looks like at 1, though the function is not defined there, the output is 2, so it's probably going to be 2. But the way we look at this analytically is by subbing in our x value that we're approaching. So for this problem right here, we can sub in 1, but you'll notice that that would result in a 0 denominator, which is not defined. So we can factor the top into x minus 1, x plus 1, all over x minus 1. And then we can divide the top and the bottom by x minus 1, which will give us x plus 1. Sub in our value that we're approaching, so that's 1. So 1 plus 1 equals 2, and that means 2 is our limit. And yes, that is consistent with what we have found graphically. Okay, points without limits. So not every point has a limit. In order to have a limit, the value that is being approached has to be the same from both sides. So that means on any continuous line in a domain, there's going to be a limit for every point. But for some functions, not every point has a limit. So some examples are the greatest integer function, which I have on the left here. At every integer, it's not going to have a limit because as you approach from the right and left, you're going to get different values. But between every integer, there is a limit for every point. Okay, in the middle, we have f of x equals 1 over x. At 0, there's going to be no limit because y is approaching negative infinity from one side and positive infinity from the other. And so they're not only not approaching the same value, but they're also approaching infinity, which does not have a limit. And then on the right, we have f of x equals sine 1 over x for all x greater than 0. This one is going to be not have a limit because the y value oscillates without bounds, so there's no limit being approached there. Okay, now we have limit laws. These can be found on pages 48 through 49 in the book, and they have examples. I'm not really going to go over much here. You can read through them if you want, but I feel like once you've read one, you kind of get the idea of all of them. And they're going to be useful for some problems, but yeah, really just read through those if you want to. Okay, eliminating common factors from zero denominators. So like I touched on earlier, our goal is to sub in the value that we're approaching to evaluate the limit, but that's not always possible when the denominator is 0. Subbing in the value we're approaching really doesn't get us anything because it's just undefined. So our goal is to use factoring or conjugates or whatever means you need to allow us to work with this and sub in our value that we're approaching. So for this problem, we'll notice that the top can be factored, so that's going to factor into x minus 2, x plus 5, times x plus 5, over x plus 5. Dividing the top and the bottom by x plus 5 will result in x minus 2, and we can now sub in our values, so negative 5 minus 2 equals negative 7, and that's going to be our limit. Okay. Using calculators to estimate limits. I'm not going to go over any examples for this, but you can use the table function on your calculator to estimate the limits. But calculators have a lot of limitations because they don't do things in the same way that we do. So there could be rounding errors and other limitations. So you're probably going to get ambiguous results on certain limits. That wasn't a great way of putting it, but yeah, just be careful when you're using your calculator. Okay, the sandwich theorem. Suppose that g of x is less than or equal to f of x is less than or equal to h of x for all x in some open interval containing c, except possibly at c itself. Suppose also that the limit of g of x equals the limit of h of x as x approaches c, and they're both L. Then the limit of f of x is L as x approaches c. That was kind of a lot because it's a very formal way of putting it, but essentially what it's saying is if you know a function is always between two other functions, then if those two other functions come together at one point, the middle function must also have a limit there. And then you've probably figured out what's going on, but I have all of my graphs highlighted in blue, my questions highlighted in red, and then I'm doing my answers in the green. So right here I have a question, given a function u that satisfies 1 minus x squared over 4 is less than or equal to u of x is less than or equal to 1 plus x squared over 2 for all x not equal to 0, find the limit as x approaches 0, no matter how complicated u is. So we don't have to worry about u at all. The way we're going to do this problem is you just have to evaluate each side of the inequality and then decide, well, if you find that they're equal, then the middle one must also be equal. So we have 1 minus x squared over 4. We're going to put in 0 because x is approaching 0. That's just going to equal 1. And then the other one would be 1 plus 0, I'm just subbing that in, squared over 2, that's also going to equal 1. So that means that the limit as x approaches 0 of u of x must also be 1. And I have a couple other examples because these problems can come in all kinds of different forms. They can have trig involved, so I'm going to do one of those. The same thing, we're just going to sub in and then simplify. So I'm going to sub in here the square root of pi plus 2 times sine, and then we've got pi over 2. Here, sine pi over 2, you may already know that. It's fine if you don't. You can just use a unit circle. That's going to be equal to 1, so this is all equal to 1. That means that this just equals pi, well, the square root of pi plus 2. Okay, the last problem here. This one is going to be a conjugate because we can't just sub 1 in here. We're going to get a 0 denominator. So x minus 1 over the square root of x plus 3 minus 2 multiplied by the conjugate, the top and the bottom. Oops, I got an eraser here. Okay, the square root of x plus 3 plus 2, change the sign, square root of x plus 3 plus 2 equals, okay, and I'm going to multiply this all out. It's going to get a little bit messy, but not too bad. X times the square root of x plus 3 plus 2x minus the square root of x plus 3 minus 2 over x plus 3 minus 4. I just skipped the middle because by design, conjugates are going to cancel out that radical. Okay, so we are, if you look at this, you're going to notice that we can't just sub in 1 here. That's going to lead to a 0 denominator. So we can factor though. So if you look here, we've got that, and we've got these. I'm going to factor those out. So the square root of x plus 3 times x minus 1 plus 2 times x minus 1 over x minus 1. Okay, this is really nice because we can just cancel, well, we'll divide the top and the bottom by x minus 1, and so that's going to be equal to 1 in the bottom. Don't have to worry about that. And then those are going to be 1s, so that's going to equal the square root of x plus 3 plus 2. We're evaluating as x approaches 1. So putting 1 in there, square root of 1 plus 3 plus 2. 1 plus 3 is 4. The square root of 4 is 2. And so that's going to equal 4 for our answer there. Okay, that's all I have. I hope this helped, and good luck on the test.